a few more examples of how to identify reactions. This should help you with today's assignment, and it's also going to help you with tomorrow's assignment, okay? Just a little sub note here is I can't make these numbers into subscripts on this app that I'm using. So you just got to know that these numbers behind here are subscripts. But that doesn't even matter because what we're doing today is we are identifying types of reactions, okay? If you watch the video notes or look through the PowerPoint, hopefully you know that there are 5 types of reactions: synthesis, decomposition, single replacement, double replacement, and combustion. Okay, so let's add a few key notes about what each of those might mean. For example, whenever I think of the word synthesis, I always think of the word building or combining. Okay, when something synthesizes, it kind of fuses together or combines. When I think of the word decomposition, I think of breaking down. So that would be like if a leaf is decomposing on the ground, if a bug is decomposing a leaf from a flower or something like that. Okay, that is decomposition. Single replacement, I feel like is pretty self-explanatory. When one thing gets replaced. All right. Double replacement, I like to think of switching places. 2 things switching places, let's say that. 2 things switching places. And then combustion, I obviously think of fire, but we also want to think of water and carbon dioxide. Okay, and that's just going to help us keep things straight if we think of fire, water, carbon dioxide for combustion. Okay, so let's look at these different types of reactions and kind of talk about how I would go about deciding which type they are. Okay, so usually I do this visually in my head, but we can also do this on paper if you have scratch paper. So what I kind of picture in my head is each element gets their own color circle. So aluminum I'm going to do with a black circle, and I will make oxygen a orange circle. So oxygen gets orange circles to go around it. So what I see now that I have everything circled is that on the left-hand side, because remember, if I split my equation down the middle, I always do it down my equal sign. So now what I'm seeing on the left-hand side are 2 separated circles. And then on the right-hand side, those circles are combined. They're touching each other. So what happened is that 2 single things came together to make one thing. And that tells me that that is going to be a synthesis reaction. Because remember, synthesis makes us think of combining or building. So 2 separate things coming together to form one thing is going to make a synthesis reaction. Okay, things combining. So let's move on to this next one and let's continue with our circles. So if I give mercury a circle, which is Hg, let's say mercury is always going to be black. I got to do it on both sides. Anytime I see mercury, I'm going to put a black circle around it. And we'll make oxygen orange again just to keep with the theme. So every oxygen gets an orange circle. Okay, and if I split my equation down the middle, down the equal sign, I can look at the different sides now. Okay, so one side has 2 circles that are touching, so they are chemically combined. The other side, the circles have been separated. Okay, so we can say that those circles split apart or they broke apart. All right, and for that reason, this is showing us a decomposition reaction because those 2 circles broke down into 2 simpler circles. So that would be what we call decomposition. Okay, let's look at this next one. I'm going to do the exact same circle process that I have been doing, and I just got to remember that each element has its own color. So if I'm doing this for Fe, let me get my circle tool out here. Fe will be black this time, so anytime that I see Fe, I'm going to put a circle around it. Okay, and then the same color. Now I have copper. Let's put it in a different color. We'll say that copper is lime green. Why not? There's copper. There's copper. It always gets the same circle. And then I need one more color for chlorine. We'll say that it is pink. Chlorine is pink. Okay, now let's split my equation down the equal sign and see what happened on either side of this reaction. Okay, so what I'm seeing is that over here, my green and pink circles are touching in together and my black circle is on its own. On the right side, it seems like my black circle took the place of green. So it looks like this black circle just went and kicked out the green circle and now it's with chlorine. Okay? So what I also see is one single circle. Okay, Haven, I'm recording this and I'm going to post a video of it. So you just keep listening along.
Oh, okay.
Does that work for you?
Yes.
Okay.
Yes.
So what I see in this reaction is I have a single circle and then two circles touching. And then on my right side, I have two circles touching and a single circle. So since it's one single thing getting replaced, so that Cu is getting replaced by Fe, that tells me that this is a single replacement reaction. Okay, now let's look at this next equation, and we're going to do the same circle technique. So let me get that out here. And let's give all of my NAs a black circle. All of my NAs get a black circle. Okay, so now let's talk about SO4. So it's on both sides, so we're going to keep it together. We're going to give it its own color. SO4 gets its own color. And then we're also going to give oxygen and hydrogen their own color. So let me get a hydrogen color. And now let's get an oxygen color. We'll go with orange since that's what we've been using for oxygen all along. Okay, so this one, I don't really have to think about that much because I see a ton of circles. If I see two or more circles on both parts, okay, there's a bunch of circles everywhere, and I split my line, my equation down the middle. Okay, so I have 1, 2, 3, 4, 5 circles, 1, 2, 3, 4 circles on the right side. Okay, there's a bunch of circles happening, and that is automatically going to tell me that this is a double replacement reaction. So the giveaway for double replacement is that there's no single circles. Okay, if I go back up to single replacement, there's a single circle here and a single circle on the right side. But in double replacement, there is no single circles. Okay, so if you don't have any single circles, it's going to be double replacement. Okay, if you don't have any single elements, even like up here in synthesis, these are single elements. Okay, then you know that you are dealing with a double replacement reaction. All right, so if it looks complicated and there's no single elements, it's a double replacement reaction. Okay, now combustion is going to be a little bit different than what we've talked about so far. I don't really look at circles for combustion. I always look at the same three things for combustion. And those three things are going to be O2, H2O, and CO2. So, this is whenever we go back to our reminder about water and carbon dioxide. Combustion always produces water and carbon dioxide. So what that means is that every time that you see just water and carbon dioxide on the right side of our equation, on the product side, you know that it is combustion. Okay? So water plus carbon dioxide with nothing else is going to be combustion every single time. Okay, you can also go one step further. If you have water and carbon dioxide as your products, you should probably also have oxygen as a reactant. And if that's the case, it's combustion. Okay, this X can be a different, a bunch of different things, which is why I put it as kind of like a variable, like you would in math class, X. So that part is going to change in a combustion reaction, but these three parts do not change. So every time that you see oxygen equals or arrow sign, water plus carbon dioxide, it's always going to be a combustion reaction. Now, with that being said, go ahead and try today's assignment and go ahead and try tomorrow's assignment as well.